Well, with the gravity given and then the length given, we're going to come up with the period for this grandfather clock, and then we use that same one in order to figure out what the length is for the second pendulum. I'm just trying to move that there. So here we would have the length of 1 meter at the North Pole, as I said, so Ln, and then we have the gravity at the North Pole. We come up with a period t, and then we have the length at the equator, and then we have the gravity at the equator, and then we come, these two times here are the same, so actually we could set them equal without even calculating the time, which we did. I showed in the animation should be 2.02 seconds anyway. And when I plug that in the calculator, let me see what I come up with. It's going to be 2 pi times the square root of 1 meter divided by 9.83 parentheses. It's 2.004 seconds. Of course, in the animation, I wasn't absolutely accurate. Okay, in any case, I'm going to set these two equal to each other. So these two here, and when I do that, of course, the 2 pi divides out, and then I can square everything, and generally I'm going to come up with this. Ln over Gn is the same as Le over Ge. And it simply means that the ratios of the lengths is the same as the ratios of the gravities. So therefore I need to figure out what Ge is. I'm sorry, not Ge. I need to figure out what the length at the equator is. So I'm going to do Le over Ln is the same as Ge over Gn. Okay, this one is slightly less than this one, therefore I should come up with something less than 1, and when you calculate this out, it's going to be 9.78 divided by 9.83, and I come up with 0.995 meters as the new length. So we would have to shorten that pendulum by half a centimeter, and I don't think that my animation is going to be that accurate that it actually could show that. This one here I'm able to put in correctly, but when it measures the time, I don't think it's going to show. It's going to show that. If there's a difference. Actually, I made a mistake again. Hold on. I need to change gravity. Oh, I already did. 9.78. So I'll start over here. And it should show the same number, but of course, you know, I'm not that accurate here. So whatever we come up with, slightly different or exactly being the same, it's not going to tell us much, because my accuracy level is not in the neighborhood of 0.5%, which is what 0.995 means. Okay, I'm almost there. Yeah, well, it shows the same number. I guess I stopped at the same time. By the way, when my animation software here, my physics software measures time, I can input that myself. It's under accuracy, and you know, I can show what kind of animation step I want. So what the time that you see here is not necessarily, definitely not necessarily the same time as clock time, because I can easily change that, and it depends on the internal clock of the computer as well. Okay. Alright, let's see. I wanted to explain what's going on there. Okay, here's the first of two reasons why the gravity is slightly different. One of them is that the Earth is not a perfect sphere. In first approximation, it is a very is very much like a sphere, but in second approximation, I guess, it's somewhat oblate, and that means at the equator it's a little bit further out, and it's still kind of a leftover from the more or less liquid Earth from billions of years ago, where as it was rotating in a liquid, the due to its inertia, where it rotates the fastest, that means in translational speed, that's where it would move to more outward, and we can definitely see that on Saturn, which is really oblate even in photos if you look at that planet. But on Earth, it's just slightly, so that means that points towards the equator are actually further away than anywhere else. And just a side note, there is a mountain in Ecuador that is actually the furthest away from the Earth's center, and therefore Chimborazo is actually kind of could be considered the highest mountain on Earth, because it reaches furthest into the sky, even further than Mount Everest. And anyway, because at the equator it's further away from the Earth's center, and gravity is, the acceleration due to gravity is calculated from, hold on, I take this back here, from Newton's second law and the law of gravitation. And the law of gravitation says that we have the gravitational constant here, and then we have the mass of something, and then we have the mass of the Earth, this is the symbol for Earth, divided by the radius of the Earth squared. This is the gravitational force as you have seen it before. And now this force here equals mass times acceleration, and then whatever mass is being attracted by the Earth actually divides out, and that's why something is falling under the influence of gravitation. Its fall is independent of its mass, and then when you plug in these numbers here for the gravitational constant and the mass of the Earth and the radius of the Earth, you come up with the acceleration due to gravity. So this one here then comes out to little g. And now if you're further away from the Earth's center, that radius of the Earth becomes larger, and therefore that g becomes smaller. And as I said, because it's oblate out here, so it's further away at the equator, that gravitation is smaller than it is up here at the North Pole or anywhere in between. That's why in Alaska we also have a relatively large value, 9.82, because we're closer to the Earth's center than we're at more southern latitudes or latitudes towards the equator. The second reason is a little bit harder to explain, I believe, so I'm going to give it a try. I'm going to put the cross-section of the Earth into, I put the Earth's surface as a cross-section here. So if we imagine that we're here, and now g is pulling us down. So here we have an acceleration g, but at the same time Earth is rotating, and due to our inertia we would want to go straight out, but of course gravitation pulls us back, and as gravitation pulls us back we have this centripetal force here, which is supplied by part of the gravitational force. So the faster we're rotating, the faster we're moving here, the larger that centripetal force needs to be, and that takes away from our local acceleration due to gravity, and that's why where we're rotating faster, the translational speed being faster at the equator, that's why that value is yet a little smaller. So we have the extreme values of 9.78 and 9.83. I acknowledge that my equation here, that my explanation here wasn't the best. So if you have a question for that, please let me know, and I try to explain that somewhat better in another recording or over email or on a discussion board or something, or in eLife.